Hi students, this is the chance to tape for computer vision course. This is a lecture on optimization that I promise that I'll be giving you through a video to replace Friday, March 28th lecture because a lot of students will not be available that day. Okay, so we're going to cover pretty much this quiz problem here, two quiz problems right here. One is quiz number 8 and the other is quiz number 9 and the other one is quiz number 10. Okay, and they're due on the 4th and the 11th respectively. Okay, so let's look at the first couple of problems. The first couple of problems in quiz number 9. Here you'd see that we are trying to fit an equation ax squared plus bx plus c. And I've already given you what the values of a and b and c should be ผมก็ให้มาแล้วนะว่า a b c ควรจะเป็นอะไรแล้วตัวนี้เนี่ยก็เป็นตารางที่ผมได้ทำให้มาแล้วนะแล้วเราต้องการ so I've given you this values of x y so given this you're supposed to try to minimize certain energy and it's very similar to the problem that where you minimize given slope mb but here instead of mb you have abc instead of mb in class we covered AB and here we do MB but it's pretty much the same problem ก็จะคล้ายๆกับข้อที่ให้ไปในที่สัปดาห์ที่แล้วที่ผมทำเกี่ยวกับ MB แต่ unknown มันจะเพิ่มขึ้นเป็น3ตัว okay so there are 3 unknowns here and problem number 2 you solve the same problem but you use the pseudo inverse okay so the pseudo inverse which I defined last week we call like that and just show it. You could use MATLAB if you want. You could use whatever you want to show. You don't have to show the source code. อันนี้ใช้ MATLAB ทำก็ได้ฉะนั้นคำตอบของข้อ1กับข้อ2เนี่ยน่าจะคำตอบ solution ก็น่าจะได้ A ประมาณนี้ B ประมาณนี้ C ประมาณนี้ so for both problems you should get values of A, B, and C close to what I've already given you here. Okay? So let's go on to this problem number 3 though is actually made up of 3 problems. It's actually solving the same problems using 3 methods. การข้อที่3เนี่ยก็คือโจทย์เดียวกันแหละแต่ว่าใช้3วิธี The first one is continuous space gradient descent. The second one is state space gradient descent, and this one uses Gibbs sampler. So this is a new algorithm that includes simulated annealing, and that's what I'll be covering today in this lecture. I've already covered this in last lecture, but I'll go over it again today. อันนี้เคยสอนไปแล้วยังเหลือเรื่องนี้กับเรื่องนี้ที่เราจะทำกันวันนี้นะแล้ว so after today's lecture you would be able to solve these problems. Now this problem is basically you're given you're given a certain image. We call it. So this is the image file. ฉะนั้นเราได้ภาพมาเป็น input นะ This is your input. And there are certain pixels that have no data มันก็จะมีบาง pixel ที่บอดไป okay so wherever there's no data your dij is equal to 1 for these points here okay so for these points you have a dij equals 1 that's one way to represent it นี่ก็เป็นวิธีแทนมันนะฮะdij เอาใหม่นะ dij จะเป็นจุดที่มี data so dij is sorry this is not dij dij means there is data so it's for these points here. All right, so we're going to minimize energy, and I've shown you this in class already. ในห้องผมก็อธิบายไปแล้วนะแล้วก็ผมอธิบายวิธีนี้ไปแล้ววันนี้ผมจะพูดถึงอีกรอบหนึ่ง so I'll explain it again today in brief detail, and then we'll go through this in a little bit more detail. 2 หัวข้อนี้เนี่ยจะมีลงรายละเอียดมากขึ้นนะโอเคก็ก่อนอื่นBefore we get into all this, I just want you to get the idea that computer graphics and computer vision are kind of inverse problems in some sense. Computer graphic กับ vision นี่เป็นปัญหาที่เป็นโจทย์ที่กลับกันนะ In computer graphics, you have a complete 3D model of the world. For example, you have a shape of the object. They tell you what color, how shiny it is, how transparent it is, what texture mapping is on it, where the light's coming from, where's the camera. So out of all this world model, you generate a video or you can just generate a single image. So ใน computer graphic เรามีโมเดลของโลกเนี่ยแล้วเราก็สร้างภาพขึ้นมา most students have not taken computer graphics, so they may not, 3D graphics, so you may not be quite aware of this. But in general, I think you know the idea that you create a 3D model and then you generate images. Whereas in computer vision, in this problem, you have a lot more data, and the projection, the images are very simple. อันนี้คือเรามี data เยอะมากเราก็แค่เอามา projection เท่านั้นเอง But in computer vision, the image is much more difficult, okay? Because the problem is much more difficult because you have an image, and out of that you're supposed to get 3D world properties, okay, such as shape or color, segmentation or identify objects, no position, track objects. So this is a much more difficult problem. ฉะนั้น computer vision ค่อนข้างยากเนื่องจาก input เป็นภาพแล้วเราต้องมาเอาจากภาพที่เป็น2มิติมาได้ข้อมูลที่เป็นโลก3มิติ So from two-dimensional images you're supposed to interpret a lot of information. So we know that we explained last time that because of the loss of information in images due to projection, projection causes a loss of a lot of information. So due to projection, we have to have some constraints to be able to give us more equations to solve this. Sort of like, it's sort of like we only have 2D, so 2 equations, and maybe this is 3D, and so it needs one additional equation at least. ฉะนั้นแบบถ้ามองหยาบๆก็คือตัวนี้เป็น2มิติก็มีแค่2อาจจะมีแค่2สมการนะแต่ตัวนี้มันก็ขาดไปอีก1มิติอีก1สมการเพื่อที่จะหาตัวนี้ได้อย่างน้อยนะ So that's one rough way of viewing it. It's like less information to more information. Therefore, you need to find some additional constraints. คือเราต้องหาข้อบังคับเพิ่มขึ้นนะคือเพื่อที่จะหา solution ได้แล้วก็จะเป็นอะไรที่ทำกันแล้วก็ในที่สุดก็จะใช้ optimization ใน image processing ในการทำ computer vision. Okay, so there are many ways of finding the best solution. Optimization, we've done regression, we've done half transform. That's one kind of optimization in some sense. It's to find the best fit, sort of line. Gradient descent, what we did last week, it's very similar to Newton's method. Newton's method is also based on gradient descent, actually. ฉะนั้นวิธีที่ Newton method ถ้าคุณเคยเรียนมาเนี่ยก็จะเป็นอะไรที่พื้นฐานของมันมาจากการทำ gradient descent นั่นเองนะ and today we're going to cover simulated annealing and Gibbs sampler. Well, simulated annealing is a general technique, but the Gibbs sampler is like a gradient descent, but using a non-greedy simulated annealing algorithm. วันนี้เราจะพูดเรื่องรายละเอียดถึงตัวนี้ And there's another class of algorithms called evolutionary or genetic algorithms, which is also non-greedy. So these three are non-greedy, okay? And I will explain non-greedy in a moment. คือเราเรียกว่า3 algorithm นี้ไม่ได้เป็น greedy algorithm คือไม่ตะกะนะ greedy algorithms are those that will always at any step look for the best solution. So it's greedy. It wants to do the best thing every time. It wants to take the best possible step every iteration, every moment. So that's why we call it greedy. But these algorithms tend to have a problem that they get stuck. Like for example, if you look at a solution, a space that's like that, and if you start over here, you will tend to take gradient descent. You will come to the best. And at here, you would think, oh, this is the best already. And this is called the local minimum. Okay? The global minimum, the best solution should be here. This is sort of like, this is energy. Okay? This is energy. And this is perhaps just x. And let's say, for simplicity, this is like energy is a function of x. So we're trying to find the best x, for example. ในข้อนี้เราอาจจะพยายามหา x ที่ดีที่สุดเนี่ยถ้าเรา greedy เนี่ยเราจะบอกว่าเอาไปทิศที่ชันที่สุดเราจะไม่หลุดจากจุดนี้เลยไง from here we are not going to go up because this is the best solution and we're just going to get stuck here, okay? And this is typical of greedy algorithms. They get stuck at a local minimum, but very often the local minimum is a good enough solution, but most of the times it's not. So you need to find a way of not getting stuck here, being able to jump out and look for a better solution. In this case, we want to look for this solution here, which is the the global minimum. So genetic algorithms and simulated annealing in general, they're not greedy, so they will find you a way that's not always the best at every step, but eventually they try to get around this local minimum problem and seek a better solution. Okay, not always the best solution at each step, but eventually it becomes a very good solution. So อาจจะทั้งทุกสเต็ปนี่ไม่ได้เอา solution ที่ดีที่สุดแต่ในที่สุดเนี่ยก็จะได้คำตอบที่ดีกว่าเนื่องจากเราหา solution ที่เป็นค่าต่ำที่สุดในทั้งภาพนี้ okay okay computer vision เนี่ยมี there are certain problems that we do in computer vision. Once we learn optimization, which is what we're going to do today, we'll be able to solve optical flow. We'll be able to do stereo vision, which is two images where you compute shape from two images. This is something the human eye does, that we have two eyes, and from two eyes we compute depth, right? You might have seen 3D movies where you use special lenses, special glasses to fuse images of the left and right eye. So this is also stereo disparity. Shape from shading is another example where through the shading you see some sort of shape. Okay. Structure from motion is when you see shape based on moving objects. Shape from texture, like you can see here, this is a regular texture, and you can see the shape here that it looks like a lantern or a lamp. So you kind of see the shape based on this texture here. Shape from contour is a very difficult problem. Shape จาก contour นี่ก็คือดูจากการวาดเนี่ยเราจะเห็นรูปทรงมันนะเราจะเหมือนกับเราเห็นรูปทรงมันเหมือนกับเราเห็นว่านี่เป็นแก้วคล้ายๆกับเป็นแก้วนะ okay and this obviously is like we also see a shape there. So and this is like we see a little bowl right there, right? So it's like 3D, but it's really actually just a contour drawing. So ฉะนั้นจากแค่เส้นวาดเนี่ยเราจะเห็นเป็น3มิติได้เนี่ยก็เป็นอะไรที่ค่อนข้างจะทำยาก okay but that can all be solved that are all part of computer vision problems that can be solved with optimization. Okay, so let's come to this problem of regression. We talked about this last week where we say if given 4 points we want to find the best fit line, find the best MB such that y equals mx plus b. So this is probably the best fit line here, and for these 4 points given 1, 2, 3, 4 here. So we express the energy function as that, and we've explained this in class already, so I'm not going to go over it in detail. ฉะนั้นนี่ก็คือ energy function ที่ได้ก็จะมีการบวกลบระหว่าง xi, yi นี่คือ data นะ data นี่คือ1 2 3 4 ชิ้น so we have 4 pieces of data, and we check the computed y, which is this, and we subtract that from the observed y. ฉะนั้นผลต่างระหว่างที่คำนวณได้กับที่เห็นเนี่ยเราก็มาดูผลต่างแล้ว square มัน the reason we square it is just because the difference can be plus or minus, it's the same, right? So this is an energy function, and we can minimize this by gradient descent, right? We want to minimize E. We want to find M and B such that you will get the minimum energy. ใช่ไหมต้องการหา MB ที่ดีที่สุดงั้นวิธีนี้เราอาจจะใช้ pseudo inverse ทำก็ได้ we can use a pseudo inverse. This is AX, we use AX equals B, and here you will see that if you multiply A transpose A, X equals A transpose B, okay, and then you can write X equals A transpose A inverse multiplied by A transpose B ใช่ไหมอันนี้ก็คือตัวนี้ก็คือส่วนที่เป็น A transpose A, and there's the inverse over there, and this part is just A transpose, and when you do this is a 10 by 10 matrix, so it can be inverted นี่คือ10 คูณ 10เราก็ inverse ได้แล้วก็มาคูณตัวนี้ มันก็เหมือนกับเราสามารถที่จะหา MB ที่ดีที่สุดได้ so this is one way that we explained last week of how to do it, right? Okay, so now I explained again, in computer graphics, it's 3D, 2D, it's easier. Computer vision, projection causes loss of one dimension of information. So it's under constraint and cannot be solved. Assumptions about the world are needed to solve such problems by adding more equations. We add some artificial equations sometimes. They're not realistic sometimes. Sometimes they're realistic. Like we could add the smoothness constraint. Smoothness constraint is often used in computer vision ใช้บ่อยมาก smoothness constraint เนี่ยก็คือเป็นอะไรที่เราเติมเข้าไปเพื่อที่จะให้มีสมการมากขึ้นนะ so the smoothness constraint is often the assumption that neighboring pixels are of the same color, and this is true for most images. Images, when you poke somewhere, nearby pixels generally have a similar color. Like if you look here and here, whatever, these pixels sort of have, similar colors. Like this whole region has same color, for example. Okay, but yeah, there's a lot of difference also. But generally the smoothness constraint, the smoothness constraint works pretty well. ก็เป็น constraint ที่ค่อนข้างจะใช้ได้นะ Now, last week we talked about gradient descent, where this is the energy terrain. นี่คือสมการถ้าเราเลือก MB สักจุดหนึ่งอาจจะ random นะนี่อาจจะเป็น M0 B0 ก็คือจุดเริ่มต้น the initial MB that we choose, whatever it is, we're going to find a way down this energy down. We're going to decrease M, for example, to head this way towards this is the ideal MB. So maybe it's like that, and this is like that. This is the value of M that's optimal, and this is the value of B that's optimal. M that's optimal right there. Okay, so initially when you minimize this energy, the algorithm, the gradient descent algorithm that I explained last week, is that you start with a random value, and then you go in the direction, you keep decreasing or increasing M or NB in the direction of gradient. ฉะนั้นเราจะเริ่มที่จุดเริ่มต้นที่ random นะอาจจะปรากฏตรงนี้นะ energy ค่อนข้างสูงแล้วเราก็จะลดค่า M ลงหรือเพิ่มค่า M ขึ้นแล้วแต่หรือ B ก็จะลดหรือเพิ่มเนี่ยเพื่อที่จะเข้าสู่ค่าที่เป็น optimum นะค่าจุดเนี้ยที่เป็น optimum ก็แปลว่าจุดที่ MB เนี่ยที่จะทำให้ energy เราต่ำสุดโอเคเราก็จะหาจุดนี้ให้ได้Okay, so this is the gradient descent algorithm. You start with a random value, whatever, you could even start with 0 actually, but we'll start, in statistics it's a good idea to start with something random so you don't bias your solution. ฉะนั้นเราไม่อยากจะลำเอียงเราก็ random ดีกว่าให้0มันก็เราลำเอียงไปทิศที่แบบอาจจะไปใกล้ๆ0อะไรอย่างเงี้ยนะso we're going to have an update. We're going to update the values of MB by moving a small step in the direction that will reduce the energy to the max. That means that we want to change the energy, or delta E should be max. Okay, delta E should be negative max. This is a ฉะนั้นโดยทั่วไปเนี่ยเราก็แค่เดินแค่เล็กน้อยในทิศอัลฟาเป็นหมายเลขเล็กน้อยนะอาจจะจุด001 it's just a small number. The step size that we want to take in the direction, this is the gradient direction. Okay, so we are going to update M. That means the next M is equal to the previous M minus alpha, and this is the direction that we're going to take. Okay. Similarly, for B, it's dE over dB. So notice that for M, it's dE over dM. For B, it's just dE over dB. So for anything, this is generic. It can be used for anything. So if you want to write xt, for gradient descent, you can just say, okay, it's minus dE over dx. So x, 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 b, b, b. So this is pretty much the update rule. This is called the update rule for gradient descent. And I explained where it comes from last week. I'll show you again here. มาดูกันว่า update rule ตัวนี้เนี่ยมาจากอะไรนะแต่เดี๋ยวก่อนที่เราจะไปดูว่ามันมาจากอะไรเนี่ยเราคำนวณก่อนเราเอา gradient descent algorithm ให้จบก่อน We're going to show you the full algorithm first. So these are random values of m and b. Initial step 0. This is when t equals 0. And we're going to find dE dm, dE dB. And remember the update rule is mt. This is where I derive it. If we let dm equals minus dE dm, and this is for those of you who want to understand this, and dB dt equals negative dE dB, this will get us in the direction that will minimize energy, okay? Decrease E fastest or quickest, okay? นี่เป็นวิธีที่จะทำให้ E เนี่ยลดไวที่สุดถ้าเราให้ dm dt เท่ากับ dE dm นะ dm dt ก็แปลว่า dm dt means delta m because delta t, each iteration is just one step. So delta m, which means mt plus 1 minus mt, this is really just delta m, right? Over delta t. ก็เลยเท่ากับลบนะเท่ากับลบdE dm. So I suppose there should be a negative here, like that. Sorry. When you take the derivative, this becomes a plus, right? There's a negative 1 here, so this becomes a plus. This is correct. And so this is the update rule for m, and this is the update rule for b, okay? This should be a plus, okay? So เราก็ได้ update rule นี้มาละนี่ก็สัปดาห์ที่แล้วเราก็คุยเรื่องนี้ไปแล้วนะ We already covered this last week. This step we're going to keep repeating. Each time we repeat, we actually get a new m and a new b. ได้ m กับ b ใหม่ไปเรื่อยๆอัปเดตไปเรื่อยๆแล้วจน we keep updating this until the system kind of gets stable somehow. ไม่ค่อยมีอะไรเปลี่ยนแปลงนะจะเป็นแค่ e ไม่เปลี่ยน m ไม่เปลี่ยน b ไม่เปลี่ยนก็ได้ทั้งหมดไม่เปลี่ยนก็ได้ So basically we want there will be very little change. The system gets kind of stable. That means it's time to stop. Okay? So just notice that อยากให้สังเกตว่าถ้าเกิด e เป็นฟังก์ชันของ mb เนี่ยเราก็จะเขียน update rule อย่างนี้ So this will be the update rule if e is a function of mb. There's m, b, b, b. Okay? If e is a function of x, y, z, there's going to be 3 update rules for x, 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 y, 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 and z, z, z. This is something you could memorize if you want, but I've explained to you in the previous slide where it comes from, okay? And I explained to you last week in class as well. And let me explain it to you here also, again. ผมอธิบายให้ฟังให้ดูอีกครั้งหนึ่งแล้วกันว่าที่มาของ update rule เมื่อกี้เนี่ยมาจากอะไร so I'll show you where it comes from. This is called the chain rule, right? This is from calculus. Actually, this should be straight dE dt like that. The chain rule means because e is a function of 2 variables. The way I remember it is kind of these two get cut and it becomes dE dt, dE dt. But anyway, these are crooked d, it's partial derivatives, and this is not a partial derivative. Okay, so we want dE dt, we want delta E with delta t to be the most negative number possible, big negative. Why big negative? Because that means et plus 1 minus et. Et is much less than, this will be negative. คือตัวเนี้ยใหญ่กว่าตัวนี้ฮะตัวนี้สูงกว่า For example, this could be energy of 100, and the next step the energy is 20. So when you subtract that, you get minus 80 because that means the energy is decreased from 100 to 20. คือเราอยากไปในทิศที่ energy จะลดตลอดนะ So we can see that if we do this, okay. If we do this and if we do this, we will get the biggest possible negative number, okay, maximum negative. So that's why the update rule is basically this is mt plus 1 minus mt, and you take the mt to the other side and you get the update rule. So this is the basis of the update rule in gradient descent. So why do we choose this update rule? ทำไมเราถึงเลือกที่จะอัปเดตด้วยกฎนี้ก็เป็นเพราะว่ามันจะทำให้ energy ตกเร็วที่สุดที่เป็นไปได้ because by choosing this update rule the energy will decrease quick as possible. Okay? Alright, so we come back to this problem here, and this is not very different from that problem that we just showed you, but here you have three equations instead. And it's not y equals mx plus b, but it's sort of like y equals ax squared plus bx plus c. So it's a quadratic equation, but I'm sure you can express it. You express the energy function, and then you will write at plus 1 equals at minus alpha de dA, for example. Okay, ก็น่าจะทำได้ก็คือ random a b c ก่อนแล้วก็ค่อยๆหา so you random a b c and then you keep looping until you find a stable solution. Okay, pseudo inverse ก็คงทำได้เช่นกัน so that you could use very similar problem that I've already shown you an example and you can solve that. Okay, so the problem in the previous problem, since it's an energy of A, B, C, the update rule, this is the update rule from gradient descent, okay, update rule, and it boils down to these three equations, okay, ก็ในที่สุดจะมี3สมการนี้นะ and if you plot each iteration time is each iteration แต่ละ iteration นะแล้วเราดู energy เนี่ยเราจะเห็นว่ามันจะตกมาเรื่อยๆจนกระทั่งมันเริ่มนิ่งๆแล้ว so once the energy stops there might be some points here where it fluctuates a little bit, and once it stops changing you know that okay พอละ it's enough, and whatever you can stop there, and whatever your value of A B and C are you report that ฉะนั้นตอนที่เราหยุดเราก็แจ้ง solution เป็น A B C ที่เราเจอในเรื่อง step size เนี่ยstep size เราเรียกว่า alpha เนาะ step size alpha เนี่ยต้องเล็กหน่อย the step size alpha should be small, and sometimes a very big step size would cause the energy function to fluctuate like that and it doesn't end. Okay, so that means the step size might be too big. You might want to decrease it. So some people after every iteration reduces the step size, like multiply alpha equals 0.9 alpha or something. เพราะว่ายิ่งไกลๆทีหลังๆเนี่ย step size มันยิ่งสำคัญเพราะว่ามันเริ่มแบบไปสู่จุด minimum นี้แล้วใช่ไหมมันก็อาจจะจากนี้มันกระโดดไปนี่ถ้า step size ใหญ่ไปมันกระโดดไปกระโดดมามันไม่เจอ minimum สักทีมันกระโดดใหญ่ไปเหมือนกับเรากระโดดข้ามหลุมอะนะ so it's sort of like we jump too big a step size and we miss this minimum, but if you go too slowly you will never miss the minimum, but you might just be crawling down very slowly. It takes hundreds of iterations to get here. So it's not a bad practice to jump fast in the beginning, and then you might your step size, then you decrease your step size and you slowly come down and you will meet that minimum point. Okay, so ก็อาจจะเริ่มที่ step size สูงหน่อยจะได้กระโดดเร็วจะได้จบเร็วนะแล้วตอนหลังๆก็เอา step size เล็กก็ได้นะอันนี้ก็ต้องลองเล่นดูsome problems the step size needs to be really small to work. Okay, so it depends on each problem. นี้เรามาดูตัวอย่างของโจทย์หนึ่ง let's look at this one example, very simple problem where this is the observed image data. Let's say this is ij given to us here. แล้วมันมี noise ไงมันมี noise อยู่ข้างใน so this data has noise in it. We want to compute Fij. This is what we want to compute, and this is simpler problem than we talked about in class อันนี้เป็นโจทย์ง่ายกว่าที่เราเรียนในห้องเพราะว่า IIJ เนี่ยก็มาจาก FIJ ผสมกับ Gaussian noise เพราะมันถ่ายรูปมา so it comes from a source. FIJ is the actual color that we should observe, but because of Gaussian noise, it gets distorted, and that's the observed eye. So our point is we want to compute Fij where we rid the noise. อันนี้อาจจะง่ายกว่าไอ้ที่ missing pixel ที่เราทำในห้องเดี๋ยวโจทย์นั้นเดี๋ยวผมก็จะอธิบายอีกทีนึงแต่นี้มาดูศึกษาด้วยตัวอย่างนี้ก่อน So let's study with this simple example. And here we use the smoothness constraint, and this is something I talked about in class. We can assume that this pixel is smooth with the next I, and this is I plus 1. They should be similar, and if you look at J and J plus 1 should also be similar. Some people might even go and do another pixel here. This would be I plus 1, J plus 1. You can even do, but here we only need two smoothness, but you can make 3 as well. คือแทนที่จะทำ smoothness แค่กับเพื่อนบ้านด้านขวากับด้านล่างเราจะทำด้านเฉียงได้ด้วย So instead of just the right and the bottom pixel, we could also go diagonal pixel, okay? And there's going to be a weighting constant here between the weight factor between data and smoothness. It's always good to divide this by the maximum possible before you square it, so that you keep this between 0 and 1, and you also keep this between 0 and 1. So you might want to divide this by 255. บางทีมันก็ดีถ้าเราให้ค่าพวกนี้มันอยู่ระหว่าง0ถึง1 lambda มันจะได้มีความหมายที่เป็นน้ำหนักระหว่าง2ตัวนี้ได้ So the lambda, will be the weighting factor, but here you might want to make it lambda with 2 because, this and this is the smoothness constraint. We also want the smoothness constraint itself to be between 0 and 1. It'll make it for us to be able to compare these two constraints to be on the same units. มันก็จะทำให้หน่วยของ data constraint กับ smoothness constraint เนี่ยหน่วยเดียวกันเราจะได้คิด lambda ได้คิดน้ำหนักได้ว่าตัวนี้น่าจะใช้มากกว่าตัวนี้เท่าไหร่ so we can weigh the lambda higher. For example, say we want to make the lambda, we want to depend more on smoothness, we might want to make the lambda 1, and this is always 1, right? This has a 1, so 1 and 1, or we could make this 1 and this 0.5, or this 1 and we don't want to depend much on smoothness, we can make it 0.2. ฉะนั้น lambda อาจจะน้อยหน่อยถ้าเกิดเราไม่มี noise แต่ถ้ามี noise เยอะเนี่ย with high noise we want to increase the lambda. This is low noise, this is high noise, and we'll talk about that, show that in the next slide soon as well. Okay, so ในโจทย์ noise removal เนี่ย in this noise removal example we have, let's say we have 100 by 100 pixels, that would be 10,000 unknowns. ถ้าเรามีภาพที่เป็นพิกเซล100 คูณ 100เราจะมี unknown 10,000 unknown เลยนะแต่อัลกอริทึมก็คือเรา random Fij ทุกจุดนะ for all ij ก็คือสำหรับ ij ทั้งหมดก็ random ทั้งภาพso we random the whole image, all the Fij first. So it looks like TV noise when you turn the TV on to a channel without any signal. It'll all be sort of random, that sound that you hear when the TV goes on. And this is the update rule, okay? So this update rule is the same, because remember the update rule when we have 3 unknowns, we would have A here, and A here, then B, B, B. But here we have Fij are all unknowns, so there could be 10,000 unknowns in this example. So we need to find these 10,000 values. So there's going to be gradients with 10,000 of them instead of just A, B, C, or MB that we did as examples. There's going to be a whole bunch of them for all Fij. So มันจะมีจำนวน gradient เยอะมากก็คือเท่ากับจำนวนพิกเซลแทนที่จะแค่ A, B, C หรือแค่ MB. Okay? So เราก็จะ repeat step นี้ไปเรื่อยๆทำไปเรื่อยๆจนกระทั่ง energy เนี่ยก็เหมือนเดิม initially the energy will be very high and we keep repeating until it kind of dies down. So this is time and this is energy, and you can see that as the energy stabilizes, that means that you found yourself a good solution. Okay, so let's continue. For noise removal example, I could even show you what dE dF is going to be. The dE dF, by partial derivatives of that equation, you will notice that we're talking about this equation here. When you take the partial derivative, this 2 is going to drop down, and then this 2 is going to drop down, and then you're going to take the derivative inside, which will bring a negative out. So I hope you remember how to solve derivatives, so that's very simple. And we've done this in class anyhow, so we get this value for the first term, and there are 2 of these terms that people just tend to forget. So I'll just say here that don't forget this, okay? And 3 exclamations will make you never forget it, right? So, okay, so don't forget อย่าลืมนะว่ามันมี Fij เนี่ยแฝงอยู่อีก2ที่หมายความว่าอะไรมี Fij แฝงอยู่ Usually when we talk about partial derivatives, since it's derivative with respect to Fij, we know that we only take terms that have Fij in them. They're only relevant. ก็คือพวกที่ไม่มี Fij มันก็จะกลายเป็น partial derivative มันก็ไม่คิดไงมันก็เป็น0. So anything without Fij will have a partial derivative of 0. But we might tend to forget that there is an Fij elsewhere. So as an example, I showed you this, like if you're gonna look for Fij is, let's say 2, 2, as an example, okay? And last week in class I also showed something like this. Notice that 2, 2 comes, from here. There's going to be, this is because of the 2, 2 itself. But there's going to be a 2, 2 that comes out when ij, this is when ij is equal to 2, 2. And this is going to be in the case when, because when ij equals 1, 2. When I and j were equal to 1, 2, you will also have a 2, 2 because this, the energy function is looking at I plus 1. And here, this also shows, so notice we have a 2, 2 here as well, and we have a 2, 2 here as well. And this case comes when I equals 2 and j equals 1, okay? So even at 2, 1, because then we have a j plus 1, the ij plus 1. I have to show you in the original equation to see that, but anyway, we've done this in class. And so hopefully you can understand that when you take the derivative, okay, I can see that partial derivative dE dF 2 this doesn't matter because it doesn't have any 2, 2s. This doesn't matter, but this matters. This doesn't matter. All this matters. This doesn't matter. This doesn't matter, but this one matters. Okay? So out of 1, 2, 3, 4, 5 terms. So we'll have 5 terms, not just 3. ฉะนั้นเราจะมี5 term ด้วยกัน 1, 2, 3, 4, 5. Okay? So มันจะมีทั้งหมด5 term. One of these signs is wrong. This should be a minus. Okay. Alright. So ก็หลักๆก็จะเป็นอย่างนี้นะ So let's go on. Okay, so it's correct here. Okay, minus, minus, and plus, plus. Okay, so the algorithm, so now we have the update rule, and it just basically it comes out of computing this correctly from this equation. We compute the derivative correctly. ก็ถ้าคุณคำนวณ derivative ได้เนี่ยมันก็คือโอเคนะเราก็ random ก่อน random เสร็จ update rule ก็เหมือนเดิมแล้วก็ทำไปเรื่อยๆ so it's the same algorithm. We random Fij for all ij, and then we use the update rule, and then we repeat step 2 until there is no change. ก็เราก็จะได้ภาพนะแต่ตอนนี้เรามาเปลี่ยนโจทย์กัน ตรงนี้เรามาเปลี่ยนโจทย์ so we're going to change this problem to cases where there is missing data. So dij means 1 means has data, 0. So these pixels will have dij equals 0. These values, okay? And we want to eventually find this. This is what we want to find: the best signal without the noise and with the missing pixels filled in as well. So we want to fill in pixels. Okay? And then we also want to remove noise. So we have two objectives here that we're trying to meet in solving this particular problem. But it's not very different from the previous problem. มันไม่แตกต่างจากข้อที่ smoothness อย่างเดียวที่ไม่มี dij ที่เพิ่งทำไปนะคือสมการมันคล้ายกันมาก all the equations are very similar. So this is exactly our quiz problem. You basically show the missing pixels as white. You take away half the pixels, but randomly, okay? And you take a nice picture, and wherever you took the pixels out, you set dij equal to 0 there. Dij equals 1 are for the pixels where data is available. Okay? So you could show the energy function as you run, and then use the continuous space is what we've already learned. This is continuous space where you have to take the derivative. This is called, because you can't do partial derivatives on a discrete space. I mean, I'll show you the state space from pretty soon, right now actually, right after this. So now we're able to solve this problem already, and this is actually, all this comes from last week's lecture anyhow. Now we get to the new material, which belongs to this week's lecture. And actually, state space gradient descent is very easy, much easier than continuous space because no derivatives are needed. So the algorithm is very simple. So for each pixel, well, first of all, you should random Fij again, okay? For all ij. That goes without saying. You random it. And then you visit each pixel. For each pixel ij, you want to, for each possible state of that pixel, see one pixel, if you look at one pixel, let's look at the image here. One pixel, let's say we're visiting this pixel right here. We want to see what is a good value. What is the best value for this pixel? Okay? That's the question. เราอยากรู้ว่าพิกเซลนี้เนี่ยน่าจะมีค่าที่ดีที่สุดที่เราควรจะวางเนี่ยคืออะไร What should be the best pixel? So we try all possible values. So we try all values. Value 0, value 1, up to value 255. Because that pixel, since it's a grayscale image, can only have values from 0 to 255. So we compute the energy when it's 0. We compute the energy when it's 1. This is actually total energy, okay? It's not just local energy, but it's really the total energy of the system. So this is, we have to recompute this whole thing. This is called energy total. คือเราจะคำนวณ total energy เนี่ยถ้าเราไปเปลี่ยนพิกเซลนี้เป็น0เนี่ย total energy จะเท่าไหร่ถ้าเปลี่ยนเป็น1จะเท่าไหร่ถ้าเปลี่ยนเป็น2จะเท่าไหร่3เท่าไหร่4เท่าไหร่ไล่ไปเรื่อยๆ so we try 0 1 2 3 4 up to 255 and then we basically look for where the energy is minimum. So we might find that E100 has the minimum energy. Maybe that's only 25, whereas this one is 28, this one is 44, this one is 79, so on. So this is the state with the lowest energy. เราก็จะหา state ที่ energy ต่ำสุดเนี่ยก็ให้ state นั้นน่ะในกรณีนี้เนี่ย S ก็คือ100เพราะว่า E 100ก็แปลว่าตอน Fij เท่ากับ100เนี่ยมันจะได้ energy ที่ต่ำสุด so this could be that in this case the S would be the state that would be best energy would be 100 because this is where the energy was minimal. So basically after we try all possible states we will choose the state with the minimum energy among all the possible states. And we let that Fij for the next iteration be equal to that value. So in this case, in this example, it would be 100 because 100 has the minimum energy. ในตัวอย่างนี้เนี่ย S ก็จะเป็น Fij ก็จะถูกเปลี่ยนค่าเป็น 100 หลังจากที่ลองทุกค่ามาแล้วเราจะเปลี่ยนค่านี้เป็น 100 สำหรับ Ij ตัวนี้ So for this Ij we're going to change the value to make it 100 right here. Okay? Because we tried all possibilities and we found that 100 is the best value. So you do this for every pixel. You do this for this pixel. You try every possibility. This pixel, every pixel. Okay, and this will be iteration 0, and from this you will get iteration f iteration 1. As you compute, notice that you're putting in the data for the next iteration. คือหลังจากที่คำนวณเสร็จแล้วเราไม่ได้กลับมาใส่ค่าตรงนี้นะเราก็มาใส่ใน iteration ถัดไป. So after you compute a value, you actually put it in the data of the next iteration, okay? And you keep repeating this, and this will be much faster than state space, gradient space. I mean, much fewer iterations, but each iteration is computationally quite intensive. คือมันจะใช้ไม่กี่รอบก็จะจบอะนะแต่ว่าแต่ละรอบมันก็แพงหน่อยเพราะต้องคำนวณ256ค่า. Because each round you have to compute 256 energy values, and each is actually a double for loop. So each time you compute energy, you have to compute the total thing. But that's not very smart if you compute the total thing. Let me show you why you don't need to compute the total thing. But right now, before we get there, this is going to be what I explained earlier. This is your random F0 ij's, so sort of like random initially. But this doesn't seem very random in this picture, but it should be random. And as we get a new value, which is f1, xy, you should put it in a different memory. You can't just update right in the same memory. It should be, but you don't need to create too many memory, or you could return this memory and create a new one, then create f2 as a new memory and use this to update f2 ij or xy or whatever. And then you create a new memory for f3 xy. It should just remember that you shouldn't be updating in the same grid. Although even when you update in the same grid, it would work. มันก็ work เหมือนกันนะแต่ว่ามันไม่ถูกหลักของสถิตินะ all right, so you could use two image memories or swap 0 1, then this becomes 1, this becomes back to 2, then 2 3, then 3 4 if you want. And that's detail, programming detail. I don't want to get into that, but I want you to be aware of it a little bit. ก็คือนั่นคือรายละเอียดการโปรแกรมมิ่งแล้วแต่ว่าก็อยากให้คุณรู้ไว้นะมันก็เป็นอะไรที่ต้องระวังไว้หน่อย Okay, so ในกรณีนี้เนี่ย energy เนี่ยเราหมายถึง global นะก็คือยอดรวมหมายถึง total energy ที่ต้องคำนวณนะก็คือ sum x y ทั้งหมด. So, but we know that if you change, for example, if you're looking at this value xy, if I change this, for example, I say, what if this value is 0? What if this value is 1? What if this value is 2? What if this value is 255? I want to find what the E would be, right? That's what I'm trying to do. So, in order to do this, you don't need to recompute all the 10,000 E's เราไม่จำเป็นต้องคำนวณถ้าเรามี x y 10,000 ตัวรวมแล้ว 10,000 ตัวเราไม่จำเป็นต้องคำนวณทั้ง 10,000 หรอก we don't have to do all 10,000 because the E is only changed locally. When I change this pixel looks at me because every pixel through the neighborhood structure or what's called a click คือ neighborhood มันก็จะตรวจแค่ตัวขวากับตัวล่าง it's looking at right and bottom. Okay, so because of this change, this guy is going to be affected, this guy is going to be affected, and obviously this itself is going to be affected. ฉะนั้นการเปลี่ยน1พิกเซลเนี่ยเราต้องคำนวณ energy มันจะมีการเปลี่ยนแปลง energy แค่พิกเซลนี้กับพิกเซลนี้เท่านั้น. So what we could do is we could take the global energy, subtract off the old values. That means we have to remember the Eij, E for each of them, and we sum them to get the total. we subtract that out and then we add the new ones in ฉะนั้นเราก็เพื่อที่จะได้การเปลี่ยนแปลงเนี่ยเราไม่ต้องคำนวณจุดนี้จุดที่อยู่ไกลๆอย่างจุดนี้ไม่ต้องคำนวณใหม่จุดนี้ไม่ต้องคำนวณใหม่ไม่ต้องคำนวณใหม่ so these pixels we don't need to recompute but we only need to recompute this pixel and this pixel given that you're currently looking at xij okay so we could just subtract the old values and put in the new values that will be your new energy total so แทนที่จะคำนวณ10,000 พิกเซลเราต้องคำนวณแค่7ค่าเอง so instead of 10,000 we only need to recompute like sort of like actually like 3 values okay instead of 10,000 so that's a smart thing to do ฉะนั้นอันนี้ก็จะเป็น efficiency นะแต่เป็นอะไรที่น่าทุกคนน่าจะรู้นะ now if your neighborhood structure is also looking at instead of just looking at right pixel and bottom pixel, you're also looking at the diagonal pixel. So that means that you're also looking at diagonally. Then there's going to be 1 pixel, 2 pixels, and another pixel here because if you change, this guy is going to get affected, you see. He's also looking at you. He or she is looking at you, right? Could be a she, and this is a he, this is a she also, I guess. He or she could be looking at this particular pixel, and therefore, you have to recompute 1, 2, 3, 4 values. So you subtract off the old 4 values and put in the new recomputed. So these 4 must be recomputed. But you don't need to recompute the whole image, not the whole image. Not 10,000, you know, if you have a 100 by 100 image, but just basically just 3 values. All right? So let's continue here. Here, this illustrates that for each state, you should also keep the energy at xy. So you should put the energy into this data as well. Keep the current energy at that point. And then for the next state, you should also keep the current energy. Because by keeping the current energy, we will be able to subtract, we call that, the current is the old, and then we recompute the new ones. Okay, and we can put that in. That way we don't have to do many computations. So we keep energy also as an image, sort of like an image, but it's really just a two-dimensional array. So we keepเราก็จะเก็บ energy เป็น array 2 มิติไว้นะ So let's move on. Now the problem with both of these gradient descent algorithms, whether it be state space, you know, the state space. Why do we call this state space? Because we're looking at each possible state, okay? Each possible state here, this state. The state possible is 0, 1, up to 255. So it's discrete states. มันจะเป็น state ที่แบบเป็นชั้นๆไม่ได้แบบเมื่อกี้ gradient descent อีกอันหนึ่งเนี่ยเราจะทำใน continuous space ใช่ป่ะมัน partial derivative อะไรมันเลื่อนเท่าไหร่ก็ได้อาจจะเลื่อน 1.2 บวก 5.5 อะไรเงี้ย it could move 5.5 or minus 1.3 you know it could move either way but in this case it only changes to the allowed states so that's why we call it state space instead of continuous space it's like discrete space okay so the problem with these algorithms I explained earlier is that, you know, if you start here, for example, randomly you started off here and it's going to come down, 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 down. Yay, you're so happy. And here you get stuck because if you go this way, it's always higher energy, so you get stuck. This is not a good solution. This is basically the energy and this is maybe a variable x, okay, that you're trying to minimize. So we're just showing it in 2 dimensions. Generally, the problem is 10,000 dimensions, or, you know, in the case of MB, it would be 3 dimensions. In the case of MB, we've seen that we show MB and then the energy, you know, is sort of some, you know, this is the energy. So this is 3-dimensional, and we could even have, once it becomes 4-dimensional, I don't know how to draw it. Maybe you do. Actually, nobody does. Becomes very difficult to draw it. But, you know, so just to illustrate, we just show it in this hyperbola. We can show it as a parabola, you know, and it can be, you know, multi-dimensional space, sort of hyperbola. anyway, the state space gradient descent, remember that we look at the energy for each possible state and we choose the one with the minimum energy. So this is greedy, okay? Greedy because we will get stuck, choosing the minimum all the time. We get stuck at a local minimum like that, So instead of being greedy, do we have a choice? Okay? Well, yes. A non-greedy solution might be ถ้าเราไม่อยากตะกะนะแทนที่จะเลือกสเตทที่ดีที่สุดตลอดเราอาจจะบอกว่าเราอาจจะเลือกสเตทที่เรามีความลำเอียงไปถึงโซลูชันที่ energy ต่ำก็จริงแต่เราไม่เลือกต่ำที่สุดตลอดแต่เราลำเอียงไปด้านที่ต่ำ so we have a bias towards but it's not 100% bias it's just like we are biased but we will consider possibly we might possibly consider other solutions okay we might possibly consider bad solutions. Okay, so but we are biased to good choices. We will consider bad ones as well. So the way to do it is we will choose a state so that a state with the lower energy has a higher chance of being chosen. ถ้า energy มันต่ำเนี่ยโอกาสที่เราจะเลือกมันก็จะสูงกว่าแค่นั้นเองขอให้เป็นอย่างนั้นแต่เราไม่ใช่ว่า energy ต่ำสุดเราเลือกตลอด so we're not choosing the lowest all the time but we're biasing it so that we choose one with if it's a lower energy it has a higher chance of being chosen a state with a higher energy has a lower chance of being chosen as a solution so this is a probability thing we're converting energy into probability okay so somehow we need to convert energy. These energies we will convert into probabilities. Okay, P1, P2, and P255, and we'll see how to do that in a moment. And this is what's called simulated annealing. Okay, simulated annealing is a technique borrowed from physics, where you start off with a high temperature, and as you run through the process of optimization, you reduce the temperature at each iteration or after a few iterations also. Generally in physics, you run with a certain temperature for a while, and when the system stabilizes, then you decrease the temperature. But generally, to get a good solution, you can keep decreasing it after each iteration. But it's slow, okay? So you keep decreasing the temperature, maybe by multiplying it by 90%. So you'll decrease the temperature. So let's look at how it works. It looks just like state space gradient descent, but the only difference is it takes the energy and converts it into probability. So the higher the energy, the lower the probability of being chosen, okay? So, but then it doesn't mean that it's just lower probability. It doesn't mean zero chance, but it just means you have a lower chance because your energy is not so good, okay? So, you try convert each energy to a probability, and this probability needs to be a probability density or distribution function. So that means that the sum, we know that the sum of probabilities must be equal to 1, right? So for all the possible states. So we divide that by the sums. So this will make the sum of probabilities. This is a normalized probability. So this will make sure that it meets this criteria. Make sureว่า probability รวมกันแล้วได้1นะโดยการเอา sum ทั้งหมดตรงนี้เอา p พวกนี้เนี่ยมาบวกกันมารวมกันแล้วก็มาหารนะ So then you sample from this probability distribution function แปลว่าอาจจะกลายเป็นว่าโอกาสตัวนี้เนี่ย 20%โอกาสเลือกตัวนี้เนี่ยอาจจะเยอะหน่อยอาจจะ 30% โอกาสเลือกตัวนี้อาจจะสัก 20% so there are other states in between that have probabilities so they all have probabilities okay now we will sample from this ก็แปลว่าเราจะเลือก state แต่โอกาสที่เราจะเลือก p 0กับเลือก p 255เนี่ยเท่ากันเพราะมันคือจุด2เท่ากัน so we have an equal chance of choosing p 0 and p 255 because the probabilities are both 0.2 but we have a higher chance of choosing state 1 meaning let the value be 1 because it has a higher probability. So basically we will sample from this probability distribution function to get the state S. And I will explain how to sample in a moment. But you know, most people already know how to do that. คือถ้าคุณเคยเรียนสถิติมาแล้วคุณก็รู้วิธี sampling อะเนาะก็แต่จริงๆก็คือ random ระหว่าง0ถึง1 random ค่าระหว่าง0ถึง1สมมุติเราได้จุด7เราก็ไปเอาค่าที่เก็บตกได้ถึงจุด7ก็ประมาณอยู่แถวๆนี้นะคงมีอะไรที่จุด7ถ้าได้จุด23 if we get 0.7 we will choose a state that's somewhere between here, okay, between somewhere here. But if we get 0.23, we will choose P1, you see, because P0 is 0.2 and then this is up to 0.5. If we add it up, and then the whole thing will be up to 1 then. I'll show you that in a moment. Basically, you choose a random number, and based on that, you find a state. Okay, and after every step, you reduce the temperature, and you go back and you repeat steps 3 to 5. So we repeat these 3 steps. Keep repeating. Okay, until it converges. So how do we do that? Well, there's still a few mysteries here. มันยังมีหลายๆอย่างที่ยังต้องไปดูรายละเอียดนะ so มันมีเรื่องที่หนึ่งก็คือว่าจาก energy เนี่ยเราเปลี่ยนเป็น probability ยังไง how do we convert from energy to probability how do we sample from the PDF okay and why do we reduce this temperature what is the temperature for so once we understand these 3 concepts we're pretty much done with this lecture okay so let's take a look at it here we go the Gibbs sampler this is called the Gibbs sampler this algorithm that we have what we do is to convert energy to probability we know that the probability is equal to E is that you know exponential thing 2.17 or 2.71 I'm not really sure I think it's 2.718 แหละนะ so we take that to the exponent of minus the energy divided by the temperature. This is a temperature which will change after each iteration. In the beginning it's high and it keeps reducing. So why we have this temperature I will also explain in a moment. But at this point we know that this equation means the higher the E will give you the lower the probability. Okay? This is just a fancy way of doing it, and it's like an exponential function. You could use a different model actually to put the bias that a higher E should get a lower P. คือเราจะใช้โมเดลอื่นก็ได้นะที่จริงอาจจะแบบว่าP เท่ากับ1ส่วน E อย่างเงี้ยก็ E ยิ่งสูง P ก็ยิ่งน้อยนะฉะนั้นเราใช้แบบนี้ก็ได้ but classically they do it this way. All right. Because you want to put the temperature in as well. With this you can't put the temperature in. So เพื่อที่จะใส่ temperature ได้เนี่ยเราใช้ exponential จะดีที่สุดเดี๋ยวจะเห็นว่ามันเป็นยังไง So in this example, for example, state 0 is 0.2 20% chance has a 20% chance. State 1 has a 10% chance. State 2 has a 10% chance, state 3 has a 10% chance, state 4 has a 20% chance. So basically what we do is we keep adding them up. This is 0.2 for the first state. Then we add 0.1 becomes 0.3. Notice we get 0.3 now. Then we add 0.1, we get 0.4. We add 0.1, we get 0.5. We add 0.2, so 0.5 becomes 0.7 then. Eventually, at the end of all states, we will have a 1 because when we add the probabilities, it can at most be 1. And then we sample, we just get a random number between 0 and 1. You can use a random number generator. if, for example, we get the value 0.43, 0.43, as an example, lies between here and here. That means we will choose state 3 as our answer. This is called sampling from this distribution function for the appropriate state. ฉะนั้นวิธี sample ก็คือว่าเราเอาจุด 2 เพราะ state 0 มีสิทธิ์ได้ 20% อันนี้ 10% อันนี้ 10% ใช่ไหมเราก็เลยเอาจากนี้จุด 2 แล้วก็อีก 10% ก็จะกลายเป็นจุด 3 อีก 10% ก็จุด 4 10% ก็เป็นจุด 5 อีก 20% ก็เป็นจุด 7 ถ้าเรา random 0 ถึง 1 เราได้จุด 43 เนี่ยมันอยู่ระหว่าง 4 กับ 5 ใช่ไหมแปลว่า state ที่เราจะเลือกก็คือ state 3 นะ if we generate a random number and we get 0.14 instead, 0.14 lies right between 0 to 0.2 here, so that means we will choose state 0. เพราะถ้าเราได้จุด 14 ก็จะกลายเป็น state 0 นะแต่ถ้าเราได้จุด 51 ล่ะ if we get 0.51, we know that it's somewhere here, and somewhere here refers to state is this seat, this slot is taken by S4, state 4. That means we're going to set fxy to 4. ฉะนั้นถ้าได้จุด 51 เนี่ยมันมาอยู่ในช่วงสล็อตนี้นะแปลว่าเราจะให้ fxy ของเราเท่ากับ 4 นั่นนี่ก็เป็นวิธีสุ่มเพื่อหา solution. So this is a way to sample to get a solution. Notice that, you know, if you look at this, it's like a, you know, all the possible values 0 to 255, okay, from 0 to 255, will have a certain chance, a certain probability of being chosen. So up to 1, the total eventually adds up to 1. So you can draw it like this, or you can view it like this. I think this is easier to understand. This is a little bit more technical to understand probability distributions and so on. But this is an example of how each one has a little possibility, and then it keeps going. It's always going to be a non-decreasing function. มันต้องเพิ่มมันไม่มีทางลดนะเพราะว่ามันต้องบวกเพิ่มไปจนกระทั่งถึงข้างบนนี้ก็คือ1สุดท้ายนะก็จะกลายเป็น1 Okay. So then the question comes, แล้วไอ้ t เนี่ยมีประโยชน์อะไร Why do we have this t? What is it for? Well, it's actually to increase the higher the t, the less greedy. Okay? The higher the t, the less greedy you are. And as soon as t becomes low, you become more greedy. It controls how greedy your algorithm is. So in the beginning, you don't want to be greedy, but as time goes by, you don't want to stay there. You don't want to be unable to report a solution forever. คือถ้าเราเล่นอยู่ที่นี่เนี่ย high t ตลอดเนี่ยเราก็ไม่ greedy เรายังไงก็ได้ anything is possible. I'll accept a bad solution, no problem. But you know, the point is you have to get more and more strict. Okay, more and more strict. So it's sort of like in the beginning you're relaxed, yeah, anything goes, you know, yeah, fine. But you get more and more strict until at the end, when t is very low, basically you're approaching gradient descent. And I'll show you how that happens in the next slide. ฉะนั้นแรกๆเนี่ยเราก็อาจจะใจดีนะยังไงก็ได้นะไม่เป็นไรหรอกหาอะไรไม่ดีก็เอาไม่ดีก็รับแต่ว่าเราก็เคร่งตอนอายุเรามากขึ้นนะตอนเวลาผ่านไปนานขึ้นเราก็เริ่มซีเรียสขึ้นนะเอาจริงมากขึ้นในที่สุดเราก็บอกงั้นไม่เอาละ gradient descent แล้วตอนนี้มันต้องถึงเวลาที่ต้องรายงานผลละ it's time to provide a report the answer we've taken too long let's get to the point and it presents a solution. Let me show you how the t affects the distribution. So let's say that we have only 3 states นะสำหรับตัวอย่างนี้เรามา assume ว่าเรามีแค่3 state ก็คือมี0 1 2 so we have only 0 1 and 2 and let's say that the energy is 2 3 and 4. Now obviously if we are going to be greedy we're going to select state 0 because it's the minimum energy, right? But we're not going to be greedy here. We're going to convert the probability into we're going to convert the energy into probability by using this function, okay? So notice this is the energy, and energy, all right? So we divide by t, and t changes, right? I'm just showing you what happens, how t controls the shape of the distribution. At t that's very high, t เท่ากับ100เนี่ยนี่คือ high นะอันนี้ก็จริงๆก็ยังถือว่า high อยู่นะยังไม่ low เท่าไหร่น่าจะโชว์อีกสักอันหนึ่งก็ยังดีนะก็ it's still considered high but lower than that and this is like a low t already. So here we have an example of a low t. Here you notice we're starting to get greedy, but let me show you what happens at a high t. At a high t, when t is high, the probability that we get are very similar, and we divide by the sum to get a, the final probability. Okay, maybe I should call these p primes because they're not real probabilities yet. They still have to be divided by the sum. นี่ก็ยังไม่เป็น p ตัวจริงเนาะมันต้องหารกับ sum เพื่อที่จะได้ p ตัวจริงเพราะ p ต้องบวกกันได้1ถูกปะ because the p's must be able to add to be 1. So what we get is all three of these have equal probability. That's bad actually. You should have some bias. They should have some bias towards a better energy, a lower energy. But here, there's no bias. This is called a random walk. When you have absolutely no bias, you're just doing random, and it's waste of time. Okay, it's a random walk state. คือยังไงก็ได้เนี่ยไปนะไม่ดีมันก็ไม่ควรจะเลือก t ที่สูงขนาดนั้นหรอกอันนี้อาจจะสูงเกินไปLet's see what this is too high a t because you're just randomly walking. You notice that when t is 10 it's a little bit more reasonable. ตอน t เราเท่ากับ10เนี่ยมันมีเหตุผลมันก็ยังมีเหตุผลมากขึ้นนะเพราะว่าจะสังเกตว่าเราเริ่มมีความลำเอียง There's a higher probability of choosing this and a little bit higher than this. This is higher than this, which is higher than this because the energy of this is lowest, second lowest, and third lowest. But still, it's not reasonable. I would like to see something like a good number would be 0.6, 0.3, and 0.1, something like that, where there's we're kind of biased. We're kind of biased towards this, but we do allow, we're kind enough to allow this, which will probably happen when t is equal to 1. This state will probably happen when t equals 1. But to get there quickly, let's say when eventually as your t becomes 0.1 ในที่สุดตอน t น้อยมากเนี่ยจะสังเกตว่าตัวนี้เนี่ยแทบจะ 99.9% เลยจะถูกเลือกSo there's a 99.9% chance of choosing this. There's a very small chance of choosing this and even no chance of choosing this state. Very low. A very small chance which will, in practical, won't happen. So in general, now we are going to basically only choose the state with the lowest energy. So notice when t becomes very low, we are fully biased towards the best energy. So this becomes, at this state, you become greedy. Okay? You become greedy. So as time goes by, you become greedier and greedier and greedier and greedier. Okay? So you can see that t controls the distribution of the function. ฉันจะเห็นว่าด้วยเวลา t ที่ลดลงเรื่อยๆเนี่ยทำให้เราเริ่มเคร่งครัดขึ้นว่าเราเริ่มลำเอียงไปทางที่energy ที่ต่ำกว่าเราเริ่มลำเอียงมากขึ้นในกรณีตัวอย่างนี้เนี่ยตอนเริ่มนี่เราไม่ลำเอียงเลยนะเราให้สิทธิ์เท่ากันเลย Here we have no bias whatsoever, but then we have a little bit bias is shown here. Maybe t equals 1. I haven't shown that. There'll be more bias shown, and at t equals 0.1, there's even. But the t doesn't come dramatically drop. It becomes 100, then maybe 99, then it keeps dropping slowly. But here I'm just showing you 3 instances as an example, 3 snapshots. ตอนนี้ผมให้ดูภาพของ t ทีละ3 ตัวนะแต่จริงๆมันค่อยๆลดนะฉะนั้น simulate annealing เนี่ยใช้เวลานานมากในการรันนะเพราะเราต้องวิ่งเล่นตรงนี้ so simulating annealing takes a long time to run. Okay, so I hope you understand the reason we have t in simulated annealing, and the reason we use this complex exponential function is because this way we could use a temperature to control the probability distribution function as time goes by. So here we go back to and visit the simulated annealing equation. We start with a T high, we randomize first, and then we convert each possible state, just like state space, but we convert it into probability, which in this case probability is going to be, the sum should be equal to 1, okay? And then we're going to sample, and I already showed you how to sample that. Then we reduce the T, and then we go and repeat these 3 steps. These 3 steps, okay? Until the energy gets stable. ฉะนั้นเราก็จะทำไปจนกระทั่งมัน E ไม่ค่อยเปลี่ยนละ okay? So let me run a video. This is not really the quiz problem, but it's from a few years ago that I found this video that would estimate an original image and also find horizontal and vertical edges. I haven't covered this in the class, but just to show you, this will give you an idea of what happens when you run such a video. Okay, now let me get rid of this pen and go to the arrow. Okay, there you go. And this was run many years ago, and the computers were much slower back then. And this is just the first iteration. It's notice that this is a random solution, which is the 0th iteration, and it'll get clearer with time. This will be our estimated. You still don't see this guy, right? This is the input image, and we're trying to estimate this image. Now this is after iteration 1. You haven't seen very much, but this stuff is extremely slow. So I'm going to jump to iteration 3. Okay, this is after iteration 3. Then I'm going to jump. Is it any clearer? No, it's still kind of random stuff. I'm going to run iteration 9. At iteration 9, you start to see this guy's head. You start to see the camera. You see some shadow lurking in there somewhere, right? Let's jump a little bit. Iteration 12. It's emerging, okay? Let's go and jump here. Iteration 17. The edges. This edge is black and white. This is a grayscale image. Horizontal and vertical edges will do an edge detection of the image so that we don't smooth. Basically, this prevents us from smoothing between edges, but we haven't covered this. It's not that important right now. The point is to see that as time goes by, from random noise, we're getting something that looks, clearer. This is after 24 iterations. And the student has captured the screen for me here, and I'm just showing that to you. 28 iterations. Notice the edge images are coming up. This is the horizontal edge, this is the vertical edge. It's coming up pretty well. And this is after 32 iterations. So you notice that the image has been cleaned up a little bit. You might see that it's a little bit blurred compared to this. And you've also detected the horizontal and vertical edges. So the video is not a quiz problem, but it's for a problem, it's a different problem. But I just wanted you to see how this thing changes with time. อันนี้เป็นไม่ได้เป็นโจทย์ในควิซนะแต่ว่ามันก็ให้ดูตัวอย่างของการเอาภาพที่มันจะเปลี่ยนไปเรื่อยๆแล้วมันจะชัดขึ้นเรื่อยๆก็เลยอยากให้ดูเป็นตัวอย่าง okay? So that should be enough for this example. Now, you might be wondering why slowly reducing the temperature will not get stuck at a local minimum. ทำไมการค่อยๆลด temperature เนี่ยจะไม่ทำให้เราไปติดใน local minimum. To imagine this, you throw marbles. You imagine you throw marbles into a hill. You imagine a mountain. I should get the pens back. Okay, you imagine that you have a mountainous terrain with, it's like mountains. It's 3D, let's say. Okay, but if I throw a marble in here, it's likely to just come and get stuck here. But imagine that you also have an earthquake, and the earthquake is like will make the marble jump away, and pretty soon it'll jump here, then it'll jump here, and it'll jump here. It might even make it go back here again, okay, because it's just shaking too much, the earthquake. If you just let gravity take over, it's gradient descent. ถ้าให้ใช้แค่ gravity เนี่ยมันจะเป็น gradient descent มันก็จะมาจอดตรงนี้แต่ถ้าเกิดว่าเรามองว่าเราเช็คระบบอยู่ด้วยเนี่ยก็คือเรามีตัว temperature ที่จะทำให้มันกระโดดออกไปเรารับ solution อื่นด้วยมันก็อาจจะกระโดดมาเจอตรงนี้กระโดดมากระโดดไปกระโดดมาแต่ว่าช่วงหลังๆเนี่ยเราจะเช็คน้อยลง in the end as the temperature goes down we are not going to shake very much so in the beginning there's a lot of activity the marble is going to go jumping here and there it might even come here first and then jump back up here but eventually when the temperature cools down it's not going to jump very much maybe hopefully it'll jump into a pit that's kind of big and minimalฉะนั้นเราก็โดยทั่ว there's a mathematical proof that simulated annealing given a right temperature decrease will always get you a global minimum but that temperature reduction schedule it's called the annealing schedule there's a mathematical proof that if you have reduce the temperature in a good way in an appropriate way in other words if you have a good enough annealing schedule you will be guaranteed to have a global minimum okay you're guaranteed to get a global minimum but that annealing schedule is unreasonable okay unrealistic nobody uses it it'll take forever but it's nice to have some math to support you so generally though people just for example what we did is multiply t equals t multiplied by 0.9 so it reduces pretty fast and it doesn't get stuck as much from experiments people have seen that but still you never know it could still get stuck here but generally what happens is when you start here it might come here but because of the earthquake that temperature earthquake it jumps so by the time the earth is starting to quake less it's coming and eventually when you get greedy it'll just settle over here so that's the whole idea behind it all right so coming back to our problem now you know how to do state space it's much easier than this okay but it's the same thing you're greedy and then you implement the Gibbs sampler where you convert the E to probability in the Gibbs sampler and then you sample from this and the conversion from E to P will depend on temperature as in the beginning you're a little bit more liberal where even a bad E you are more willing to consider it but as time goes by the temperature goes down you become more and more greedy and you will only consider good probabilities so ด้วยเวลาที่ผ่านไปเนี่ยเราจะลำเอียงแล้วเราก็จะกลายเป็น greedy ในที่สุดนะในกรณีของ algorithm ของ Gibbs sampler with simulated annealing okay soอย่างหนึ่งที่ผมอยาก one thing that you have to be very careful about is it's very easy with this number to be this number is usually big so a negative big will make this approach zero very quickly okay so ในเมื่อสิ่งที่เราต้องทำเราต้องระวังว่ากลายเป็นว่า probability ทุกตัวเนี่ย p 0 p 1ถึง p 255เนี่ยit's possible that they become overflow numbers and all become zero okay because of overflow and then you're not able to divide by zero obviously so to avoid this sometimes it's best to instead of taking E and putting it in this equation you take each E and you minus the E min first okay and then you do the probability it will not affect because by minusing each with an E min it's just like dividing it by a constant the Z factor will normalize the probability anyway you can always divide this by any constant it still remains the same so การที่เราวิธีนี้จะทำการที่เราเอา EI ไปลบกับ E min ก่อนที่จะเข้า probability เนี่ยจะทำให้ probability พวกนี้มันไม่ศูนย์หมดไงมันจะมีค่าบ้าง 0.00001 0.00013 and then you'd get numbers like this, and then but then you could, from this, once you convert it to probability, you might get 33%, 33%, 33%, something like that. But the point is, you want to subtract by some number first, so that you don't want to get all probabilities to be zero, because if this E is big, it tends to tends to zero very quickly, because exponentials, you know about exponentials, the problem with that, right? Okay, so we're done. Aren't you glad? I'm glad. Okay, so hopefully you could do this this problem, and it's the same. You're implementing this problem, but using 3 different techniques. Okay, and later on we'll talk about using GiveSampler or using this or this to solve various computer vision problems. You can even use genetic algorithms. Actually, they're all the same. It's just a way of optimizing. Once you know the energy function, you can you can call it fitness function if you're talking about genetic algorithms. But it's all pretty much the same thing, and I'll show you a little bit of that. Okay, so we're done, and I hope you learned something and you're able to do your quiz based on this. หวังว่าคงทำ quiz ได้แล้วนะ สวัสดีครับ bye